Good afternoon. Happy Monday. So just a few reminders. So what I'd like to talk about today are OSHA regulations. So we're going to focus on indoor air quality, but we'll focus more on or entirely on the work environment. And hopefully this provides you some information as you move into the work environment, or if you are working in a lab or have an internship, you get a lot more information in this regard if you do have an internship, but I think it's useful for you to have some understanding of it as a civil, chemical, environmental engineer. Paracelsus in somewhere in the early 1600s made the, 1500s made the statement that what is it that is not a poison? All things are poison and nothing is without poison. It is the dose only that makes a thing a poison. And what I have here is a safety data sheet. It is for something that can be combustible in a dust form. High concentrations may irritate eyes and the respiratory tract. It has a slight health effect, slightly flammable or moderately flammable. Suggestions that in the lab you wear goggles, a lab coat, and proper gloves. Anyone want to guess what this is for? This is a safety data sheet. We'll look at a number of safety data sheets, but anyone want to guess what the safety data sheet is for? Something you have in your home? It is for sugar. We don't think of sugar as needing a safety data sheet. I don't, but it does. Water has a safety data sheet. As is stated here, it's the dose that makes a thing a poison. Now, when we look at exposure limits, there really are two sets of exposure limits we look at. We look at exposure limits for occupational exposure. Basic assumption there are that we're setting limits for whole, healthy adults. These adults are in the prime of their lives and they're exposed during the work day, but they can go home to a exposure-free or contaminant-free environment. When we're looking at these types of regulations, they're set by OSHA, which is the Occupational Safety and Health Administration. And then we have regulations for the general environment. These, in the case of air contaminants, are set by EPA. Now, we actually don't have any indoor air regulations set by EPA. All of the regulations we have, we'll talk about these in a few weeks, are set for ambient air. But when we set these regulations, we're setting these regulations to protect the most sensitive, the most vulnerable populations. So we're looking at protecting infants, the elderly, those that are immune compromised, those that have health conditions that would make them more vulnerable. And the assumption is that there is no escape from exposure to this ambient environment. So those are some really basic differences between the types of limits that we set. Now, most of what I'm going to focus on today is really protecting worker safety. What do we need to consider? How do we protect worker safety? And how can you, as someone who will be moving into the work environment or maybe in the work environment right now, protect yourself by knowing the regulations from harm in such an environment? So the first thing I'm going to mention are these safety data sheets. They used to be referred to as material safety data sheets. In about 2018, there was a agreement made across the globe to standardize the language, and you'll see some pictograms to standardize these pictograms. And you saw what happened in Bhopal, India, where information that was needed that would have protected workers didn't reach those that could have made changes, that could have implemented protections, or those that needed the protections. So all chemicals that are manufactured, imported, sold, used in any manufacturing process in the US must have a safety data sheet, and that safety data sheet must be available for all workers. And this is under what is referred to as the Emergency Management and Community Right to Know law. And this pertains to anything. It pertains to the custodian has the right to know what chemicals they're in contact with when they're cleaning. If you are working in a lab, you have the right to know what chemicals you're in contact with. These safety data sheets are extensive. The numbering is actually the numbering for the safety data sheets. And as I mentioned, this is an agreement that has been made. It was made through the UN to harmonize this information across the globe. So section 1 identifies what is the contaminant. We'll actually walk through a safety data sheet. 2 identifies the hazard, and we move through composition, first aid measures, firefighting measures, essentially everything you need to know in terms of from the moment you receive that chemical, if it's shipped, or are first in contact with that chemical, to disposal of that chemical. This is a safety data sheet for silica sand. So you can see section 1 identifies the substance. In this case, it's really a mixture of substances, but it identifies this as silica sand. All chemicals have a CAS number. So this is a identifier that is standardized and then can be used to identify that chemical. So even if the name is different, the CAS number is always the same. So as I mentioned, there's this globally harmonized system. It's a globally harmonized system of classification and labeling of chemicals. And this provides information on what is referred to as hazards and then precautions. So the hazards, again, this is universal across the globe. If a hazard has a number between 200 to 229, that identifies the physical hazards associated with that chemical. 300 to 399, the health hazards, and then finally 400 to 499 are the environmental hazards, so the effects on ecosystem. The precautionary statements provide you with information on how to prevent or minimize adverse effects to human health or the environment from these hazards. So based on the physical hazard, it will provide you information on how to prevent exposure, how to respond to a spill, how to store that chemical, and how to dispose of it. This globally harmonized system also provided a set of hazard pictograms. Chemicals are identified with these pictograms. Often labs will be identified also. In fact, they have to be identified at the entrance to the lab with pictograms specifying what is present in that lab. So for instance, my lab has a gas cylinder, so I've got to have that pictogram on the door. The gas cylinder also has a pictogram. If the chemicals are harmful to the environment, then the dying tree, dead fish, pictogram will be on the door, will be identified on the chemical. So again, these are provided, they're consistent across the globe. So no matter where you go, if you see a skull and crossbones, you know that that chemical is fatal or toxic if swallowed or inhaled. Continuing on, this is again is the pictogram for silica sand. So notice we've got an exclamation mark. We can go back. Low level toxicity. Typically, where you'll see this is when it's an irritant. So it's a respiratory irritant. You can see that right here. And then you see this other symbol, and that tells you that it is let's look back here, it is a health hazard. And you can see again in the numbering system, it says may cause cancer if inhaled. Prolonged damage to lungs through repeated inhalation. Issue we mentioned when we talked about health effects was silicosis. So silicosis is an inflammation of the tissue, causes scarring within the lungs, and causes significant breathing problems. So now you can see also these are the precautionary measures. So it provides you information with if you inhale it, what do you do? Get the person to fresh air, get them away from the exposure. Seek medical advice if person who was exposed feels unwell. Gives you exposure information here about protections that you can do to minimize exposure. Wash your hands after handling. Wear eye protection. Do not breathe dust. So these, again, if we're looking here, you can see we're talking about prevention. How do we prevent exposure? And then we can even talk about disposal, which you see here. Now, when we talk about exposure limits, there's really 3 sets of values that you'll see mentioned. We'll look at in the safety data sheet. There are what are referred to as threshold limit values. These are set by the American Council of Government Industrial Hygienists. These are recommended. Okay, so they're non-enforceable, although individual states can adopt these as regulatory limits. So they can be used for regulatory limits, but on a federal level, they are recommended by ACGIH. There are threshold limits for about almost 700 chemicals. Now, the recommended exposure limits are set by NIOSH. Now, the Centers for Disease Control is the overseeing body for NIOSH. And NIOSH is the National Institute of Occupational Safety and Health. It is a research arm of CDC. OSHA, on the other hand, is a regulatory body under the Department of Labor. So NIOSH and OSHA are under 2 different agencies within the federal government. NIOSH determines the recommended exposure limits so they can provide that information to OSHA. OSHA can then adopt that information. On the other hand, that rarely happens. In fact, OSHA has actually never adopted an REL from NIOSH. They will set their limits, but they've never adopted an REL. OSHA sets the permissible exposure limits. So OSHA limits these are enforceable, and they're set by OSHA. And there's far fewer. It's only about 200 or so that have been set by OSHA. So we go from recommended TLVs. Typically, these will be for 8-hour exposure. Same here. And typically also your PELs will also be for 8-hour exposure, although we have different limits that have been set for different exposures, and we'll look at those. Any questions so far? So again, we have silica sand. And again, note here, we have a threshold limit value. This TWA is a time, we'll look at this just a bit, a time-weighted average. Rarely will the concentration be constant throughout the day. So these regulatory limits are actually set based on what are referred to as time-weighted average. We'll talk about this limit here. This has to do with an immediate health risk. Notice it's quite a bit higher. And then we have the NIOSH recommended exposure limit. Again, this is set at a time-weighted average. And then we have the OSHA limit. The problem we'll look at actually uses the new rule on exposure limits. And what I've also provided you here is some other additional information, again for silica sand. It's from a different safety data sheet. But you can see, again, we've got the American Council of Government Industrial Hygienists, TLV. We also have exposure limits that are set for the EU, for the UK, and for France. So these exposure limits will vary. The Organization of Safety data sheet is consistent globally, but the limits will vary by country. So as I mentioned, time-weighted average. The concentration that one is exposed to will vary with time. So this time-weighted average is just a weighting to determine the average concentration over a typical work shift. And that's typically 7 to 8 hours. We will use 8 hours as the consistent averaging time. So we have a situation here. Recent testing was conducted during routine laboratory work, and the results revealed an airborne dust load of 2,180 micrograms per cubic meter. So that's the dust. The dust was determined to be 18.8% crystalline silica, and that results in a silica concentration of 410 micrograms per cubic meter. The 2018 silica rule set the permissible exposure limit, the PEL, at 50 micrograms of silica per cubic meter averaged over an 8-hour day. And the action limit was set at 25 micrograms of silica averaged over an 8-hour day. That action limit meant that if the levels were greater than that, averaged over an 8-hour day, then one needed to take one additional precautions and also needed to monitor the health of the workers to ensure that they were not succumb to adverse health effects. So the question that we would need to ask under this situation is, what is the maximum time that an employee can remain in the lab during an 8-hour workday based on these standards, this 2018 silica rule So if we have a PEL of 50 micrograms per cubic meter, that's equal to our concentration. We're going to assume that the concentration is constant. The time interval, what we're looking for, over an 8-hour. So if we solve this, the time interval is 0.975 hours or 58 minutes. So what that tells you is that under this situation right here, if this were the condition, that worker can remain in this environment for no more really than 57 minutes. So 58, they're going to be at that limit. That's the most that they can stay in that environment. So the second question is, what protective gear, what PPE do they need? Again, here's the safety data sheet. What does the safety data sheet say? It says, one, these are the engineering controls. We want to ensure adequate ventilation. We want to avoid dust production. In the case where there is dust production, you want dust-proof clothing. So you want some sort of, for instance, like a Tyvek suit that your workers can remove after exposure. So they're not bringing home that dust. They're not transporting it to another location, into their car, onto public transport if they're taking public transport. Protective goggles, see that right there. If there's insufficient ventilation, then they need to wear respiratory protection. And if there's a high dust protection, then you're actually going to have them in self-contained breathing apparatus. So this tells you exactly what is needed in this kind of an environment. Tells you you should need to wear impermeable protective gloves. There's your protective goggles. So in terms of working with a chemical, this provides you all the information you need. So for instance, you are taking 312, 337, where there's significant potential for exposure to dust. Tells you what type of controls, what type of PPE you can request when working with silica sand or in any sort of laboratory. Now, the other thing is that OSHA actually only applies to workers. May seem kind of goofy. It actually does not apply to students because OSHA is actually occupational exposures. Although at MSU, the commitment is that students would need to be, the same level of protection needs to be available to students as to a worker. That distinction isn't made in the university environment, at least not at MSU. In terms of what protective equipment do you need? Dust masks, for instance, are unacceptable for silica. There are a number of types of face pieces. These are reusable respirators. One has to be fit for one. So in order to actually wear one has to be medically approved by it. And MSU, it's by EHS, Environmental Health and Safety. You're actually checked medically, you're fitted for one, and that is your face mask that you would wear. And then you can also have powered air purifying respirators that can be used to prevent exposure. So because of the issue with silicosis that can occur with repeated exposure to silica dust. What I've given you here is just a table showing you the regulatory limit and the recommended limits for a number of chemicals. So what you see here are the OSHA permissible exposure limits. Notice it's in parts per million and also in milligrams per cubic meter. The conversion here is for a pressure of 1 atmosphere and a temperature of 25 degrees C. Specific conditions, as we've learned with the conversion. So all of these are 8-hour time-weighted averages. And you can see here in California, these are the California OSHA PELs. They can set their own limits. So for instance, if you look at acetone, acetone is 1,000 for the federal limit, but 500 for the California limit. On the other hand, the NIOSH recommended limit is 250. The American Council of Government Industrial Hygienists is also 250. Companies can adapt the NIOSH RELs. They can adapt the ACGIH TLVs. They're not mandated to do it, but they can. And ACGIH has developed these because they felt that the federal limits were not sufficiently protective of human health. Now, there's other limits in here. There's steels and ceilings. We'll talk about those kind of in the next few slides. So what is referred to as steel, these are short-term exposure limits, typically for a 15-minute exposure. It's mandated under federal law that these cannot be exceeded anytime during the day, even if the time-weighted average, or the PEL, for the 8-hour exposure is not exceeded. The goal is that you don't exceed these steels. If you do, they should not occur more than 4 times a day, and there should be at least 60 minutes between excessive exposures. So if we go back and we look at these, where in this case, we have a steel level for acetic acid. So we're in California. Our PEL is 10. The steel is 15, so we cannot exceed that 15 limit for more than 15 minutes, not more than 4 times a day, and there has to be at least 60 minutes between successive exposures. And the other thing is that from a regulatory perspective, you can't rotate employees to avoid exceeding that steel limit. So you can't actually make a concerted effort to avoid it by simply rotating employees. What does that mean? That means that the company has to take the proper procedures, proper engineering controls to ensure that the steels are not routinely exceeded. And you can see it, I referred to this in the previous one, but in this case, we've got benzene. So you can see here, the 8-hour PEL is 1. The steel limit is 5. And you can see that California has adopted the same levels. On the other hand, you can see very different levels set or developed by NIOSH and ACGIH. And these will be lower, they're more protective than the OSHA PEL. Now the ceilings are a level that should not be exceeded at any time during the day. If instantaneous sampling isn't feasible, then the sampling has to be as short as possible and can't exceed 15 minutes in duration. So you can see here for the ceilings, we've got a ceiling for chlorine. Maximum 1 part per million. You never want to exceed that limit. California sets it at 0.5. And then we have what is known as the IDLH. These are immediately dangerous to life or health. Basically, get the heck out of there. These are an environment that is harmful to your health. Just being in that environment is harmful. These are set by NIOSH. So they're not regulatory limits, but they are limits that are required or that are set to protect human health. These are environments that you don't want to send someone into without self-contained breathing apparatus. This could be, we talked about with oxygen limits, could be an environment that has less than 19.5% oxygen. You don't want to send someone in that environment without proper equipment, without self-contained breathing apparatus, because you don't want them passing out and somebody else gets to go in. You've got another person to rescue. These are the values set for a number of chemicals. So for instance, for carbon monoxide, it's 1,200 parts per million. There are specific regulations for sending someone into this kind of an environment. For instance, you need to have visual, voice, or signal line communication so that you know that if someone is in harm's way, you can get them out of that environment as quickly as possible. You always have to have another employee monitoring that employee that's actually in that environment. We didn't always have these. So mentioned in one of my participation questions, both my dad and my grandfather worked in the water and wastewater industry. My dad was an electrician, was sent down into pump stations years ago. He was sent down alone. There was no one standing watch. There was no one monitoring the levels of carbon dioxide, carbon monoxide, methane, hydrogen sulfide, etc. in the air in the pump station down 50, 100 feet below ground level. Thankfully, he made it out alive each time. But because people didn't, we've created these protections to try and ensure that every worker that has to go in such an environment can come out alive, can come out healthy, and doesn't succumb to the exposures. We also talk about equivalent exposures. So here, these are set for mixtures of substances where the target organ is the same. That's critical. Looking at exposure over an 8-hour period. And if the equivalent exposure is less than 1 for the aggregate of exposures, then the combination is within limits. And we'll do an example problem, which should help. So we have a situation here. We have a worker that is exposed to acetone, N-butyl alcohol, and benzene. And we have the exposures in parts per million. We also have peak concentrations, and we have the TLV, time-weighted averages, for these substances. So we're going to use the California OSHA PELs. For acetone, it is 500 parts per million, and butyl alcohol 101 for benzene. Now we can look at the steel concentrations here. This is the 15-minute, not exceeded more than 4 times. Hasn't exceeded the ceiling, but did exceed the steel value. Did not exceed it for benzene. So assume that there's one exposure. So we have some issues there. Given this situation, what needs to happen? You're the plant manager. What do you advise? Basically looking at housekeeping measures, looking at what engineering controls can be put in place to minimize these higher concentrations. When do they occur? They only occur during certain processes. Okay, well, if they only occur during certain processes, then we can start thinking about how can we modify that process in order to ensure that that concentration is below the steel. So we need to determine first what the time-weighted averages are for each of these chemicals. So for acetone, the time-weighted average is equal to 200 parts per million times 2 hours plus 600 parts per million times 1 hour plus 300 parts per million times 1 hour. And these values coming right off of the table from the previous slide, plus 700 parts per million times 4 hours. And that is equal to 512.5 parts per million. The time-weighted average over TLV, TWA, or that PEL that we've talked about, is 512 parts per million divided by, let's go over here, it's 500, and that is equal to 1.0. That's greater than 1. Actually, even without exposure to any other chemical, we've already exceeded this equivalent exposure. So we actually already know we're in trouble. For the N-butyl alcohol, we'll do a similar set of calculations, and I forgot an O in there. And that is 150 times 2 plus, and I apologize for the extra lines, 1 plus 50 times 1 plus 50 times 4. Again, these values are coming right off of this table, so it's right from here. We'll divide that, and I forgot to divide it here by 8. So we needed to divide that by 8. We'll divide this by 8 hours, and this is 0.8125. So at least at that, for this, for N-butyl alcohol.
Note the correct answer is 81.25, as will be explained later.
And we have 3 times 2 plus 0.5 times 1 plus 1 times 1 plus 0.25 times 4. Divide that all by 8, and that is equal to, I apologize, this is 81.25. This is equal to 1.0625. The PEL was 100, so if we take 81.25 divided by 100, that's the 0.8.25. So that's parts per million. So I apologize there. And we'll look here, PEL is 1. So if we divide this 1.0625, divide by the PEL, and that is 1.0625. So that is greater than 1 here, which is greater than, which is our cutoff for the equivalent exposure. So we have actually two chemicals here that even without exposure to any other chemical, we have a problematic situation that would need to be resolved.
I have a quick question.
Mm-hmm.
Can we go back to the equation for EM really quick?
Yeah.
Okay.
So it's a sum, basically, the next step that I would do, okay,
Thank you.
is I have now, I'm just going to change colors real quick. So I have this value here, okay. I have this value here, and this value here. Those are the values that I would sum. So assume if the target organ were the same for all three chemicals, I would sum those. Is it and is it less than 1? I'm already in trouble with this situation because I have two chemicals that this ratio is already greater than 1. Now the question is, can I sum them to determine an equivalent exposure? You're going to determine that by looking at section 11 of your material safety data sheet. That provides the toxicity. So that tells you what the target organ is. So for acetone, it's not classified as having a target organ. N-butyl alcohol, the target organ is the respiratory tract, and for benzene, it's a human carcinogen. So the target organs are different. So we have for acetone, we have an EM, we calculated of 1.025. For N-butyl alcohol, we calculated it as 0.8125. And for benzene, it is 1.0625. So because the target organs are different, we won't add them together. If they all did have the same target organ, then we would sum them and evaluate it. Is that value greater than or less than 1? In this case, this is greater than 1. We need to take action, implement some sort of engineering controls, or put in PPE. Ideally, engineering controls are better than PPE. PPE is the last resort. If you can't protect your employee with using engineering controls, then you need PPE. And in some cases, you're going to need PPE no matter what. And then for benzene, again, this is greater than 1. So we're going to look at what can we do to minimize exposure.